Okay, great. Yeah, so I hope all of you are doing fine. And special thanks to Manoj and Bhavanida for inviting me to give this talk. Okay, so yeah, so I'm going to talk about eigenstate entanglement entropy in PT invariant non-Hermitian system. So just a second. Yeah, okay. Okay, so first, I guess this first slide is kind of redundant right now, especially after Carl's amazing introduction to the PT invariant system talk. And okay, so here, let me first introduce what I mean by the PT invariant system. So as we can see, this P represent parity operator and T represent the time reversal operator, okay? And now these operators are defined by their action on the position and momentum as follows. So x goes to minus x and p goes to minus p when you operate this parity operator. And this time reversible operator actually change p to minus p and any I, a complex number, to minus I. Okay. Now, in general, when we talk about a PT invariant system, what we actually mean is that let's say you have some Hamiltonian H. If that Hamiltonian commute with this PT operator, then we say that, okay, so this Hamiltonian is PT invariant. And you can also have a situation where this Hamiltonian could be non-Hermitian. So one of the, I guess, one of the famous example of such Hamiltonian is this, which Carl also pointed out in his talk. You can see you have just harmonic oscillator and you have this I alpha x term. Okay, so so that's fine. But what I realized is that there is something which we don't appreciate that much when we learn quantum mechanics, is that when we talk about some operator, let's say O, and if that operator commute with the Hamiltonian or some operator H, we usually say that, okay, this H and O both have simultaneous eigenstate. But it is true only when this O is a linear operator. Okay. So now in our case, where I say that the PT, the Hamiltonian is PT symmetric, but this T is actually an anti-linear operator, right? So that means that even if, let's say, you have this system H, which let's say commute with this PT, and that does not guarantee that this H and PT will have the simultaneous eigenstate. Okay. So it turns out that actually you can have two type of situations. So one we call a PT symmetric phase, where obviously since the PT invariant system, so H will obviously commute with the PT operator. But if this H and PT both have this simultaneous eigenstate, then you have this complete real eigenvalue spectrum, even if this H is non-Hermitian, which means that if H is not equal to this H dagger. Okay. So this we call actually a PT symmetric phase. Okay. And when you have a situation, so when your Hamiltonian or I mean this H commute with the PT operator, but let's say your H and PT don't have this simultaneous eigenstate, then at least one pair of the eigenvalues will be complex, and they show up actually in the spectrum as some complex conjugate form. Okay. So this is usually what happens in a PT invariant system. Either you will have a PT symmetric phase depending on this condition, and you might have a PT broken phase depending on this particular conditions. Okay. So now I'm going to talk about kind of a, I mean, condensed matter perspective. So essentially, let's first talk about a two-side model. So the idea is that you have, let's say you have two sides, this and that, and you allowed some hopping, okay? And this hopping amplitude, you can think of some minus t or something. And you put these two sides actually in some chemical potential, and you assume that those chemical potential are, let's say, complex chemical potential. And in order to make your Hamiltonian, let's say, PT symmetric, what you can do, you can, let's say, put some I gamma. Okay, sorry, I mean, I put G here, but what I mean from this equation is actually I gamma. And you can put some minus I gamma chemical potential for these two sides. And you have, let's say, some mirror here. So this actually, I mean, this particular system obeys this PT symmetry. And you can write down this in the fermionic creation annihilation language in this simple form. Okay, so where the C's are essentially obeys the usual anti-commutation relations and so on and so forth. Okay, so let's just start with this particular case. And now if I just write down this 2 cross 2 matrix, it will be just of this particular simple form. And now you can easily diagonalize this guy, and you will see that your energy will be something like square root of 1 minus gamma square. And from here, you can obviously conclude that obviously when gamma is less than 1, your spectrum is completely real. And when gamma is greater than 1, your spectrum is completely imaginary. So from here, from just the spectrum, you can say that, okay, so when gamma is less than 1, I have a PT symmetric phase. And when gamma is greater than 1, I have a PT broken phase. And as a matter of fact, you can actually also compute the eigenstate corresponds to this E plus and E minus, and you can easily verify that these are also simultaneous eigenstate of this 2 cross 2 Hamiltonian as well as the PT operator. Okay, and that's good. And that happens only when gamma is less than 1. And now, so our idea was actually, as a condensed matter physicist, just to write down some lattice model, and go to the thermodynamic limit and try to see whether you can talk about this PT symmetric phase and then the entanglement entropy and so on and so forth, which I will discuss as I go along. So first guess I would, just motivated from this two-site model was just putting minus 1 to the power j in each side. Just put this kind of on-site potential in each side. And this also from the similar, as I discussed earlier, in the similar spirit, you can easily convince yourself that it's also obeys this PT symmetry. But it turns out that you actually can solve this model, and the energy dispersion will have this simple form going to the momentum space. Okay, and this k r just can be defined as this way, where this s are just some integer, and this happens because you are using some open boundary type of chain. So you are using open boundary condition. And if you believe in this particular equation, you can see that when your gamma is less than twice cos k, for any value of s, you have again a complete real eigenvalue spectrum. Okay, so you should have a PT symmetric phase. And now, if you really want to make all the eigenvalues real, then you would guess that, okay, so you should have you should put s is equal to for which this cos k has a minimum value. So you put s is equal to L by 2, and then if you do some trivial step and some trivial algebra, you can convince yourself there's a gamma threshold. Which I mean that below this gamma you have this PT symmetric phase, and above this gamma you have this PT broken phase. This threshold is actually in the thermodynamic limit, appropriate thermodynamic limit, it's essentially scale as pi by L. So this is a bit problematic because you see, in the thermodynamic limit, it means that you don't have a true PT symmetric phase. Okay, of course, if you talk about the finite size system, you might have, but that's not our interest is. So that means that this model is in the thermodynamic limit don't have a proper PT symmetric phase. And even though this is a PT invariant model, the H commute with the PT. Okay. So then what we did, we said that, okay, good. So if I really put chemical potential on each side, things are not looking so promising. In that particular context. So why not just put this chemical potential or this or on-site potential just to two sides, maybe in the middle one and the next middle one. And then you can think of you are putting some mirror or you are allowing some reflection in the middle of your chain. So you can convince yourself that even this model, where I just put this on-site potential only in two sides, this is also a PT invariant model. Okay, so this also commute with the PT, this H. And the way we, since now it's not a 2 cross 2 matrix anymore, so we do a numerics and we try to see whether we can understand is there any PT symmetric phase or not in the thermodynamic limit. So things we plotted here is essentially number of complex eigenvalues divided by total number of eigenvalues. Now, as I told you that, of course, in the PT symmetric phase, you will have all the eigenvalues should be real. So then I expect that this guy should be 0 in the PT symmetric phase, whereas in the PT broken phase, it will be non-zero. I mean, of course, even if one pair get complex eigenvalue in a full spectrum, that is also a PT broken phase. But in this case, what I see something remarkable is that you see from 0 to 1, it's completely 0, which means you have a PT symmetric phase. Whereas as you increase your gamma above 1, you see a complete discrete jump, and you see all the eigenvalues are become complex. So it's a PT transition happening here from PT symmetric to PT broken phase, and it's kind of a discrete jump. So it's fine. I mean, but still we have the PT symmetric phase. Okay. So then we play around even more. I mean, we just now added one more term in the on-site potential. So before I added on-site potential in the L by 2 sites and L by 2 plus 1. Now I added two more. So now I have 4 sites which are having this particular type of chemical potential. And now I see, so you see now in the inset, again, I see a nice, even if you change your total system size, you see a nice PT symmetric phase where your I is 0. And also in the large gamma limit, you see your I is 1. I mean, this parameter is 1. But in the in between, you see also a PT broken phase, but this is slightly different than the previous one, because now you have some parameter regime where you have some finite number of real eigenvalues and rest of them are complex. So that's why it's kind of having a smooth transition from 0 to 1. Okay. So we see that, okay, this in particular, this type of setup, you actually can talk about this PT symmetric model and PT symmetric phase and PT broken phase, and you can, I mean, you can do many things which we usually do in the context of condensed matter. So
yeah, I had a question. So in the previous slide, suppose the number of the next slide, if you start adding more sites, almost of the order of L, then you essentially lose. Then you completely go to PT broken phase. Is it?
That is precisely true, and that's why I started with this, because that was my first motivation, because I want to put a chemical potential on each side, and then if you do a crude calculation, you can convince yourself that actually this gamma threshold is actually scale as pi by L. You see.
Right. But in the next slide, so as long as you have just finite number of finite number of sites which have chemical potential, you will always have a PT symmetric phase. Is that
that is my guess? But of course, I mean, now this phase will be, I mean, kind of shrinking, so it will be a bit difficult to, I mean, you probably, I mean, yeah, I mean, that's my guess. I mean, if you have some finite thing, you, no matter what, you will have probably some gamma threshold where you have a symmetric, and but again, it's I don't have a concrete proof of that, but it's just a numerical observation. I mean, yeah.
Okay, thanks.
Oh, great. Okay, so I mean, so let's now come to the main part of the talk, because I mean, my title slide suggests the entanglement entropy of this non-Hermitian system. So let me first introduce to you, I mean, what do we mean by the entanglement entropy for, let's say, Hermitian system. Okay, so let's say you have some system which has some dimension L, and you prepare your system to some pure state psi. So your density matrix looks something like this. And now let's say you divide your system in 2 parts. So essentially we say that your system is bipartite. So you write down your Hamiltonian in HA cross HB. And then you just, if you just traced out all the degrees of freedom of this small subsystem, you get, I mean, in this case, if you trace out everything in B, then you get the reduced density matrix for this subsystem. And then, of course, I mean, now you have different measure of entanglement, and one of the common measure is this von Neumann entanglement entropy, and which is defined by particular this formula. Okay, so for this talk, I am mostly concentrated on this von Neumann entropy. So let's not talk about the other measure of the entropies. I mean, entanglement entropy. Okay. Now, for the non-Hermitian system, actually things are slightly more complicated, because in the non-Hermitian system, we know the left and right eigenfactors are not same. Okay, so this is slightly different from what we do in case of Hermitian system. So as a matter of fact, if you have a non-Hermitian H, then you can write this guy as some En and psi r psi l in this particular way, and where this psi l psi r actually obeys these orthonormalizations, and you can always choose your psi r to be 1 when you have the same index. Okay, so this is essentially what you had if you somehow can diagonalize some non-Hermitian Hamiltonian. Now, of course, once you have this left and right eigenvector, now the question you can ask, you can define some expectation value of some operator in this way, where you essentially sandwiching your operator to right and left eigenvector, and that will correspond to something called this density matrix, which I defined as rho LR, okay, which is defined in this particular way, and that will correspond to the entanglement entropy, which is again I defined as S superscript LR, okay. Now, of course, there you can use another definition, which is just you say that, okay, I am only interested in this right eigenvector, so I define my operator or some expectation value of some operator in this fashion, and then that will implies to some density matrix rho R, and which will be given by this particular form, and that will give you something called this S of R, which is the entanglement entropy corresponds to your only right eigenvector. So in general, you can have these two possibilities. Okay. Now, the question, we again, going back to this particular Hamiltonian I just introduced earlier, which has a nice PT symmetric phase and also a PT broken phase. And I just wanted to see if I really construct some anybody ground state of this particular Hamiltonian, just feeling, let's say I mean, let's work in the half filling. So let's just assume that I am populating just lowest L by 2 number of energy single particle energy state. And then what I see is something remarkable happening here. And if I really focus on this right entanglement entropy, then I see something really interesting happening in the PT symmetric phase. And it is that you see that it started with something, and this is essentially corresponds to the Hermitian limit result. And at the one, I mean, at the transition point, this guy actually going to 0. Okay. And oh, one more thing I wanted to point out is, given that it's a non-Hermitian system, it is not obvious that your entanglement entropy will be always real. So we also check that, and it turns out that in the PT symmetric phase, your entanglement entropy is just real. So imaginary part is just 0. Whereas as you go to the PT broken phase, you start having this imaginary part start kicking up. Okay. But this result is really fascinating because you see at the transition point, the right entanglement entropy goes to 0. And that's why we conjecture that, okay, why don't we try to get our result starting from some Hermitian model? And obviously, since given the fact that at this transition point, this guy is 0, the obvious guess was something like this. So where you have just tie binding, just nearest neighbor hopping Hamiltonian up to this side, L2 by 1 minus 1. And rest of the site also you have a tight binding hopping. And only thing is that when you have this L by 2 sides and L by 2 plus 1 sides, and there I put this variant, the hopping parameter I just changing in this way, and that's particular functional form is just motivated by this particular variation of my entanglement entropy. Okay. And what we found is something remarkable, that if you take this particular Hermitian model, okay, and try to calculate the entanglement entropy, this dashed line corresponds to that, and it matches absolutely brilliantly, okay, with the non-Hermitian data. And then we again go back to this two-side model, which we did in the beginning, and we try to understand that what is happening and why the two things are matching with each other. And we found something remarkable is that actually, when you have this two-side model, you also can construct something called the C operator. And that operator is something which commute with this Hamiltonian, this 2 cross 2 Hamiltonian, and also the PT operator. And in this particular simple framework, you can show very easily the C operator will have this particular simple form. And then again, thanks to a work of Bender in 2001, is that one can do this mapping, and this mapping between this non-Hermitian Hamiltonian and the Hermitian Hamiltonian, and you can do it only in the PT symmetric phase, as a matter of fact. And this mapping, you can write down this, you can do this mapping in this way, okay, just following this expression. And if you really do this computation for 2 cross 2 matrix, you will see that actually your Hermitian matrix will have this form, and this is precisely the form I had here. So just for the two-side model, you don't have anything in the on-site, and you have this particular variable hopping only when you are thinking of this, this L by 2 sites and L by 2 plus 1 site. So this kind of give us a motivation that why this model, this Hermitian model, is a good equivalent model for the initial non-Hermitian model we started with. Okay. So then we did not stop there. We then looked at to the typical states, entanglement entropy for the typical states, where essentially the idea is again the very simple. You just populate L by 2 number of single particle state, but you just do it randomly and then take some random realization many times. Okay, and it turns out that again the SR, the right entanglement entropy, actually obeys a beautiful volume law, and which is also kind of true if you really in the Hermitian limit as well. Okay. Now we come back to this S of LR thing. So essentially now I'm constructing entanglement entropy from this left and right eigenvector. And what again in the Hermitian limit, I know this my model. I mean, when I say Hermitian limit, I mean gamma is equal to 0 limit. I know my model is actually gapless. And if your model is a gapless, we know the ground state can be mimicked with some kind of CFT, and the logarithmic, and you see a logarithmic scaling with the system size of this entanglement entropy. And as a matter of fact, for the open boundary case, it should obey something like this type of expressions. Okay. And where this C is just a central chart. And for the particular choice of Hamiltonian we worked on, the central chart should be 1. Okay. So what we have found here is that even in the non-Hermitian limit, where your gamma is non-zero, you see that actually this scaling works, and which essentially is telling you that this type of gapless features which was there initially in the Hermitian limit, it's still there even if you break the hermiticity. Yeah. But also we found something even more interesting is that at gamma is equal to 1 point, which is the special point in the sense that where you have this transition, the scaling is actually much faster than anything compared to this logarithmic. Even it's much faster than much faster than the linear. Okay, so and we looked at it even more carefully, and what we found, or what we concluded, that actually the scaling here is actually exponential, because we plot in the semi-log spot and it looks kind of it's kind of exponential at the transition point. Now also we played the same game and studied the typical state and I mean entanglement entropy for the typical state, and there also we see that in the PT symmetric phase it obeys beautiful volume law, and at the exactly at the transition point the scaling is much faster than the volume law. Okay, so as a matter of fact that concludes kind of our result, which says that of course, I mean, you see all this beautiful scaling, but also in the transition point, if you define some quantity like entropy density, entanglement entropy density, which is defined as some S of LR by L, that guy will be diverging as L tends to infinity, because the growth of SLR is much faster than anything compared to linear. Okay, so this is one beautiful result. And also now I'm almost done. So it's just, so recently we are working on the similar type of setup, but adding interaction. And what we are finding is remarkable is that as you switch on interaction, actually your PT symmetric phase again shrink in. And so this is a kind of a rough phase diagram which we are getting. I mean, this work is still in progress with Bhabani and another student here. So yeah, so this is something we are presently working on. So, okay, so now let me conclude. So we essentially discuss a PT symmetric non-Hermitian lattice model. We talk about Hermitian equivalence of this model, and we talk about different entangled measure, SR and SLR, and different scaling for this PT symmetric phase. And also we said that we found that this entanglement density actually diverges at the transition point. Okay. Yeah, so yeah, that's it.
Yeah, thanks Ranjan.